Okay, so today I will show you how I created this custom-made LED ring light that you can use to spice up your project using the potentiometer or the rotary encoder. And it's very similar to my previous project where I was using this LED ring light module, but a lot of people were saying that while this module is nice, it's way too expensive, and pretty much everyone was saying that if I make it on my own, it will be much cheaper. So let me tell you right now how much those two modules cost, so you don't have to wait until the end of the video, although if you wait until the end of the video, it will be much appreciated. You can buy this LED ring light on AliExpress for about $20, but I think that a lot of people haven't realized that this is the price for 2 pieces, so one piece is slightly below $10. As for my custom-made module, this was manufactured by PCBWay, who is also a sponsor of today's video, so thank you PCBWay. The price for this module was $63 for 10 units, which means $6.3 for one LED ring light. This price included the custom PCB, then the assembly cost and all the components, in this case that's 32 LEDs. Those are white SMD LEDs and the package is 0402. This is one of the smallest LEDs that you can get. So the answer is yes, you can get something similar a little bit cheaper, but obviously we are not comparing apples to apples because this LED ring light also has the nice enclosure. And if I would add this to my module, I would use 3D printing for a few of the pieces, or maybe something like the injection molding for more pieces, and it will definitely increase the cost a little bit. By the way, you can get both the 3D printing and the injection molding from the PCBWay as well. Let me talk about the price a little bit more. Here you can see that for 10 sets, the component cost was $16, the assembly was $30, and the PCB was $17. And if you've seen any of my other videos, I usually say something like you can get 10 PCBs for $5, and if you use the link down in the description, you can get them for free, only paying for shipping, which still holds true. So why my PCB cost is $17 and not $5? Well, that's because I needed the assembly, and my PCB was simply too small to put inside a pick and place machine. So the PCB has to be penalized, and that increased the cost. Here is a photo of the penalized version, so 2 PCBs are placed next to each other so they can be easily put inside the pick and place machine. You've probably already looked into the next columns. If I would need 100 of those modules, now the price will be only $3.9 per unit, and if I would need thousands of those, the price will be below $2, so $1.7 per unit. But I don't really need that many ring lights, so I'm left with $6.3 per unit. You've also had to add a fraction of the dollars for those header pins, which I've soldered to the PCB, and just like the last time, I'm using this module on the board with the Max 7219 chip. This chip is usually used to drive those 8x8 LED matrix displays, but I'm using it to drive this 32 LED ring light. If you are not sure what's going on, I would suggest you to watch my previous 2 videos which describes in detail how multiplexing works and also how this chip works. Actually, the Arduino sketch that I have from the last time will not only work for the LED ring light module, but also with my new module. And that's because the connection is the same. So let me go to KiCad and show you what changes I made to the previous PCB. This is what we have from the last time. If I open the 3D viewer, we have a place for the potentiometer in the middle, and then there is a place for the LED ring light around the potentiometer. I have tried to put the labels for all the individual pins, so for example pin C4 is a common cathode number 4, which goes to pin C4 down here, so those 2 header pins will be connected to the main board to the Max 7219 chip. All the connections between the LED ring light and those header pins are on the front side of the PCB. On the back side of the PCB there is only the connection between the potentiometer and the header pins for the potentiometer. Those 2 pins in the middle are only to keep the potentiometer in place. If I go back and open the schematics, we have the potentiometer connected to the header pins and then the LED ring light, a custom component connected to those header pins. And since we want to replace the LED ring light module with the individual LEDs, I will delete all the wires and the LED ring light and instead place the LED by clicking this add symbol. In the filter type in LED and select this common LED symbol. If we want, we can also select a footprint in here, but I will just click the OK button, place it anywhere and then go to Tools, Assign Footprints. Yes, I can annotate it and assign the footprint from here, so go to LED SMD. And the advantage of doing it like this is if I select the footprint and click this icon, I can not only see the schematics, I can also click this button and show the 3D viewer so I can see it in 3D. We want to use the LED with the footprint 0402, one of the smallest LED you can get, but there are still 2 footprints, one for hand soldering, this one has slightly bigger pads, and the other one for the pick and place machine. You can see that those pads are slightly smaller. I will select this one, double click it to assign it for the LED, click the OK button, rotate the LED by pressing the R key like so, And then we need 32 copies, so I'll move this potentiometer down here and create 32 copies of this LED. I have grouped the LEDs by 8 because every section of 8 LEDs will share the same common cathode. But before I connect those, I will annotate the schematics by going to Tools, Annotate Schematics. And this order section might be a little bit confusing because I want to annotate it going from left to right. And that's actually the second option, the sort symbols by Y position. Click Annotate. It should go from 1 all the way up to LED number 32, which seems to be the case. And now I can connect those LEDs. Every first LED in the group will be connected to pin L1, so D1 will be connected to pin number L1, as well as D9, also D17 and D25. The second LED will be connected to pin L2, so L2 is up here, so L2 will be connected to LED number D2, also LED number D10, then the LED number D18 and D26. In the end, it can look something like this, and then we want to connect the common cathodes. Those are the pins C1, C2, C3, which is up here, and C4. For the first group, all the common cathodes will be connected together. And then to pin C1 down here. The common cathodes for the second group will be connected to C2, this will be connected to C3, and finally this to C4. In the end, the schematics might look something like this. Obviously now the PCB is not matching the schematics, so I will go to Tools, Update PCB from Schematics, click the Update PCB and click the Close button. Now I have those 32 LEDs which I will place somewhere. I can delete the LED ring light and I can probably also delete all the old connections by going to Edit, Global Deletions, select the D tracks and wires on all the layers and click the OK button. Yes, I want to delete everything, but I still have those zones being pre-filled, so I right click and select the zones, unfill all zones. It also looks like that some of those labels were not part of the LED ring light footprint, so I will delete those manually, one by one. Now we have the PCB without any connections, and we can start placing those LEDs. Unfortunately, I still haven't found a way how to put elements around the circle in KiCad easily. I mean, there is an option in the right-click menu called Special Tools, Create Array, and you can create a circular array, but this function is creating copies, which is not something that we want. We want to reposition the current elements. Then I found a plugin which is called Place Footprints, and you use it by selecting first component, in our case that's D1, I will find it and select it and maybe move it to the side. And then I can run the plugin, so run the plugin Place Footprints, place by reference number. It will automatically select all the corresponding footprints going from D1 up to D32. I want to create the circular array and I can select the radius and the angle, and if I click the OK button, it looks almost perfect. However, I don't want a full circle like this. I want the first LED to start around here, so like this, and then continue around the circle like this, and the last LED might be around here, so there will be a gap down here. All of that to match the potentiometer, which doesn't rotate 360 degrees. And that seems to be a problem. I wasn't able to find any settings that will produce such a result using this plugin, so I was again on square one, and I have to manually position those elements. I mean, almost manually. I first measure the distance between the center and one LED, which seems to be around here. Open the properties, and the radius seems to be around 9.7 millimeters or so, so copy this into clipboard and set it back to 0, 0. And then right click and select Special Tools, Move Exactly, and if we check the Use Polar Coordinates, we can set the distance, angle and rotation. So the distance will be our 9.7 millimeters, and the rotation should start at 120 degrees. Click the OK button, and this is our first LED. After all the LEDs are on the correct positions, the PCB might look something like this. You can see that I also rotated the footprint for the potentiometer, otherwise the LEDs will not fit. So we have the LEDs on the board, but nothing is being connected, and we can of course select this tool Route Tracks and start routing the tracks, so this will be connected all together for the first 8 LEDs. This will be connected to pin here, and it's quite simple to route tracks in KiCad, but with so many LEDs and so many pins, it will definitely take a lot of time. So what I will do instead is to use a dedicated plugin, and the plugin is called Free Routing. Now when you run it, if you don't press this cancel button, it will start routing automatically, which I guess is fine, but if you don't want to do this, you can press the cancel button and then set the settings. I will most likely start with default settings anyway, and then click the Start Auto Router button. And then you just have to wait depending on the complexity of your design. But I know that you don't have time, so I will speed it up for you. This process took around 2 minutes, and in the end everything is connected. You can see we have quite a lot of vias. Those are the small holes connecting the front and the back of the PCB, but with 32 LEDs on the very small space. That's kind of expected. I wanted to see how the routing would look like if I don't restrict those connections to a 45-degree angle, which I can set in the settings, so settings, routing, and set the snap angle to none, but unfortunately this wasn't working as expected. I kept it running for a few minutes and it ended up on pass 26 with at least one failed connection. I'm pretty sure there might be a setting that can fix this, but I haven't found it yet, which means that I will stick to 45-degree angle connections. I have also two zones, one for the front and one for the back, which I will fill by right-clicking and selecting zones, fill all zones. By the way, those zones are not connected to anything. And this could be the final version of the PCB, so this is the front of the PCB and the back of the PCB. You might have also noticed that I've moved most of the labels to the back of the PCB. You can do this easily in a KiCad by selecting something and then pressing the F shortcut, and that will move it to the front, and pressing it again will move it to the back. I wanted to make the front as clean as possible, only keeping those small dots for LEDs. Those are the cathodes, but I don't think that those are needed for the pick and place machine. It's more a reference. Exporting for manufacturing could be done by going to File, Plot, selecting the Gerber files, then click the Plot button, then click the Generate Drill Files and generate the drill files, close it, and then go to File, Fabrication Outputs, and generate the components placement, the position file. In here I have selected Include Only SMD Footprints because I only want to place the SMD components. Click the Generate Position file, close, and it's time to upload it to the PCBWay website. I have kept most of the settings to default, only changing the solder mask color from green to black, since it looks better and it doesn't affect the price. If I would want to go with matte black, it will be slightly more expensive. Then I've scrolled down and also added the assembly service, sent it to PCBWay, and then it was time to wait. And after a week or so, I have received my boards and they look great. One thing that is hard to see when working in KiCad with a huge magnification, on the big screen, is the size of those components, especially those LEDs. They are very tiny, but at the same time quite bright. Thankfully, the used chip, the Max 7219, can set the brightness in 8 steps. Actually, it's 16 steps, but I'm only using the first 4 steps because then it gets too bright and I'm worried that it will damage the LEDs. Same as the last time, I've made it a PCB that you can not only put the potentiometer from the front side, but you can also put it in from the back side because there is a hole in the PCB. And if you bend the pins, you can still solder it. Now, the last time I've told you that it wouldn't be possible to put this on the Max 7219 board because there is not enough space, but that's actually not true. If you carefully remove all those small metal pieces from the potentiometer and bend this capacitor a little bit to the side, you can still fit it in there. And I think that this placement is better because now the knob is much closer to those individual LEDs. I do have a version where the potentiometer is mounted on the top and it doesn't look that nice, but the option is still there. Now let me talk about two more things, and that is how to get those boards, those modules much cheaper. And that's simply by soldering those components by yourself. You can only order the PCBs and the PCB stencil from PCBWay, then you can get the reel of 3000 LEDs on AliExpress for about $21, which means that the price for one LED is 0.007, or for 32 LEDs that's around $0.23. Then you can get this mini hot plate preheater on the PCBWay for around $100, and this should be big enough for our PCB, since it has the size of 5 by 5 centimeters. You will probably also need a pair of tweezers and some solder paste. You can do the math by yourself, but if you don't mind placing those small tiny LEDs with tweezers, you can save some money this way by not ordering the PCB assembly. The last thing that I wanted to talk about is this video titled Arduino Robot Eyes, because in that video I was testing the LED matrix display and it was using the multiplexing chip called AIP1640. This chip is not only cheaper than the Max 7219, but it can also drive twice as many LEDs. You can control 128 LEDs, and this chip also uses the I2C connection, which means only 2 wires for the data. I will definitely try to use it in my future project. And that's pretty much it for today. If you have any questions or comments, please put those down in the comment section. Thank you very much for watching, and I hope to see you soon. Thanks and bye.